Hello, BC Calc. This is your day 74 notes. Today we're talking about the derivatives of inverse functions, which we really haven't talked about yet because we needed to know certain rules before we can get there. But before we get right into that, there are two warm-up questions here. One is bringing back some work examples, and the work example at the top here is referring to something called Boyle's law. Boyle's law states that the pressure is inversely proportional to the volume. So you can read through the question. A quantity of gas has this initial volume and a pressure of 500 pounds per square foot, and then it expands to a volume of 2 cubic feet. What is the work done by the gas? So just to help you get set up initially here, if pressure is inversely proportional to volume, then the pressure is equal to some constant K divided by the volume. Okay, so directly proportional would be K times V in this case, but inversely proportional, we get K over V. So we know, just like we've done in other work examples with Hooke's law, we got to find the value of K first. Once you find the value of K, then you can set up a definite integral to determine the work. So go ahead and try that one. I think once you get to the stage where you found K and you're setting up your integral, you'll know why we had to wait till this part of our unit to do a question involving Boyle's law. If you look at the question at the bottom, find dy dx for this equation. Definitely thinking some logarithmic differentiation here, but I didn't write it up above, but I do want you to try both of these questions before I see you next in class. See if you can use the properties with logarithmic differentiation to come up with the derivative there. Okay. What we're going to go on to in the next part of our lesson is kind of building the concept of how do we define E. And we're going to get into the calculus of E in the next two lessons as well. But there are three main ways in which we can define E that might be beneficial for us depending on what we're trying to do. So in the first instance, E can be defined as the input for the function ln of x such that the output there is 1. Okay. So it's the solution to ln of x equals 1. If you were to plug in an input of E, the ln of E gives you an output there of 1. A few different ways to justify that. There's what the graph would look like. Okay, so once you have that in your notes, a second way to define E is based on an accumulation function. And if you input E for that upper bound in the accumulation function, E is what we plug in to get an accumulated area of 1 underneath the curve. And you can justify that by finding the antiderivative. We know antiderivative 1 over t is ln absolute value of t. Plug in the lower bounds of E and 1. And we know ln of E is 1. According to what we have above, ln of 1 is 0. So therefore, we do get that the accumulated area, when plugging in E to the accumulation function, is an accumulation of 1. And finally, our last definition involves a limit, as you can see in number 3. And this is something that we'll prove later on in chapter 7. But the limit as x goes to infinity of 1 plus 1 over x to the x is E. And I'll tell you later on, of course, this eventually leads us into things like, compound interest formulas where interest is compounded continuously. So we have to wait a little while. Or later on, we might even see this equivalent that we can sort of rewrite this expression here that we're looking at here and take the limit as x approaches 0 from the right of 1 plus x to the 1 over x power. So we're not going to quite talk about this yet, but we'll see a proof of this later on in chapter 7 as to why the limit as x goes to infinity of 1 plus 1 over x to the x is E. And thinking just a little bit more about E here, what is the relationship between e to the x and ln x? Well, hopefully we know what the relationship is. We can justify it in a few ways. One way to justify a relationship here that I want you to come up with is actually by composing the two functions. So I'm going to do one composition where I take ln x and sub it into this function over here. I'll call that y1. So y1 is going to be e to the ln of x. And then y2 is going to be the ln of e to the x. And what you'll find is if you graph both of those on the calculator, let's see if mine will be cooperative here. If I graph e to the ln x and I hit zoom 6, we get just that little linear looking function there, e to the ln x. Looks like y equals x to me. Okay, but it's only y equals x under certain conditions, right? So for our first example, we're getting y equals x, but only if x is positive. And then in the second case, if I type in the ln of e to the x, ln of e to the x, we're going to see the negative part of the line y equals x, but also, if you can't quite tell, it is copying over the positive side as well. So for y2, we do wind up getting that y equals x. So what happens is when you compose a function, or compose two functions, and in both directions, you get y equals x. Now here we have a little bit of a domain issue, right? So we can only plug in values here for the natural log functions that are greater than 0. Here, when you're taking the natural log of e to the x is always positive valued, which is why we can plug in negative x's and get the entire line y equals x. But when that happens, when you do the composition in both ways, and in both instances, you get an output of x, we know, and you probably knew this in advance anyway, but these two functions are inverses of one another. So that will really help us, I think, over the next couple lessons here to start determining derivatives and antiderivatives with respect to e to the x. We're not quite there yet. Let's start exploring the relationship between derivatives of inverse functions. So if we take a look at this chart below, where we have three different functions given, y equals f of x. We're going to find the derivative of each. We're going to find the inverse of each. And then we're going to, excuse me, find the derivative of the inverse and see if we can make some conclusions as we go down the line. So for the first example, if this is f of x equals 2x, then f prime is actually just the constant function 2. F prime of x would be 2. If I really quickly find the inverse by switching the x and y values, x would equal 2y. So if I divide the 2 over, y would equal x over 2. So the function g of x is equal to x over 2. And if g of x equals x over 2, then its inverse, or sorry, its derivative would be 1/2 using the power rule. So we do just have to be careful. You can see I already made a quick mistake that you're going to look at these quickly and think, okay, this means inverse, this means derivative. So make sure you're finding the right thing in each column here. But we're going to mix those notations up. So we want to make sure we're confident with what we're being asked to find. Y equals x squared, only for x greater than 0. Maybe you remember why we have to kind of restrict x squared to be only when x is greater than 0. But the derivative there, f prime of x, would be 2x. And if we find the inverse, switch x and y, so we get x equals y squared. And then square root, we know that the inverse is g of x equals the square root of x. And if I find the derivative of g of x, g prime of x, using anti-power rule, this is one that, I think we found the derivative of radical x so often. I'm hoping you can jump pretty quickly to that derivative there. But if not, use the power rule and get 1 over 2 radical x. Okay. So we want to start kind of building a connection between the derivative of the original function, the derivative of the inverse, and see if there's any kind of connections there. Okay, so moving on to the last example, x cubed plus 5x plus 2. Well, the derivative would be 3x squared plus 5. And the inverse would be, oh boy, x equals y cubed plus 5y plus 2. I mean, I'm not quite sure how I'm going to get y alone there, so I'm going to put a question mark. And because I don't know how to get y alone there, I'm going to put a question mark for g prime of x and leave that one for another day for now. Okay, so if something's not easy to find the inverse of, what we'll find later on in this lesson is we can actually still evaluate on the inverse function. We can still find g prime of some value, even if we don't have a definition for what g prime of x is. Okay, or g of x, I should say. So let's talk about if f of x and g of x are inverses, does it follow that g prime is 1 over f prime? So are the values here simply just the reciprocals? So it kind of looks like that way for number 1, like f prime is 2, and then g prime is 1/2. So, and that would always be true for the function y equals 2x. Is that going to necessarily hold true for example 2? So in example 2, let's do something that we can easily calculate. So for example, f prime of 4. So f prime of 4 would be 2 times 4, which is 8. So is g prime of 4 the reciprocal? Well, let's check that out. So g prime of 4 would be 1 over 2 radical 4. And since the square root of 4 is 2, we get not 1/8, but we get 1/4. So we're not quite following that rule here that maybe we thought was going to be the case, that when we're finding a derivative of an inverse function, it's 1 over the derivative of the original. So we have to develop another pattern, and I think the best case scenario for us to develop this other pattern is to look at this from a graphical perspective. So on the next page, I'm going to have you draw a graph, and we're going to use example 2 as kind of a guide here to be able to determine what's going on here. But a couple things to fill in quickly before we get on to the graph below. It says in order for us to develop a rule, we must be working with one-to-one functions. Hence why I define x squared to be only where x is greater than 0. Otherwise, that is not a one-to-one function. It's going to be tough for us to talk about the derivative of an inverse. So some classic non-one-to-one functions would fail the horizontal line tests: sine x, x squared, y equals 3. Here are some good one-to-one functions that we wouldn't have too many issues with: radical x, x cubed, linear functions. So graphically, what I'm looking for is exactly what I just referenced. For one-to-one functions, we're looking for them to pass the HLT. And algebraically, the concept is that if f of a and f of b are the same, then a equals b. Okay. So if two outputs, I guess, have the same value, then those inputs must have been the same in order for us to have something that's one-to-one. We don't want an input to, or I would say, I guess, two outputs to belong to the same input or vice versa. Okay. So the picture that I'm going to have us draw is considering the example from number 2 on the prior page where we had x squared where x is greater than 0. What you're going to see sketched below, if you want to start making your own sketch, is what that looks like on the interval x greater than 0. And I'm going to graph the inverse, which is radical x. And you're going to get something that looks like this. Okay, so my blue graph is x squared where x is greater than 0. And because I showed you that if we look at f prime of 4, the slope of the tangent line there is 8. And that corresponds with the point 4, comma 16. We saw that g prime of 4 is not the reciprocal. So when I look at this inverse function, if I were to plot x equals 4 and draw the slope there, we would find it's just not a relationship with the slope at x equals 4 on the original function. So maybe you can kind of see where we're headed with this. You can see I've identified the corresponding location on the inverse, that 416 would correspond with 16,4, right? We know that any coordinate pair on a function would represent, if I switch the x and y values, a point that is on the inverse. So it turns out that to get that reciprocal relationship that we were kind of exploring, it turns out that if I have my two functions, f of x and g of x, graphed above, whose derivatives are the following, that we can get those slopes to be reciprocals if I do the following inputs. So what we find here is that f prime of 4, which we calculated earlier to be 8, is going to correspond with g prime of 16. Okay. So the reciprocal slope relationship here is that if I look at the slope of a tangent line at any given point on the original graph, we know that the reciprocal slope is going to be on the x value that corresponds with the output here, right? Because when I switch those x and y values to get now 16, comma 4, we find that this slope is the reciprocal of this slope right here. So for this specific example, we know that g prime of 16 is equal to 1 over f prime of 4. So to find the derivative at a specific value on an inverse function, what we're going to do is we're going to look at the output of the original function, right? When we plug in 4 to the original, the output is 16. The reciprocal then of that slope is going to represent the slope on the inverse there. So in general, we get something that looks like this, that g prime of x is equal to 1 over f prime of y. And I think this will make sense when we put it into practice here. So the next 2 pages are just practice. I'm going to do some of them with you, and then I think after we've done some examples together, we'll leave some to do in class next time we're all together. Okay. So if you have all that down, let's take a look at our first example, and it is the example we were just looking at. So I'm going to kind of go through this one a little bit quickly. So we know that in order to find the inverse g of x, we would switch x and y, solve for y again. But since we've already done this for x squared, we know that the function g of x is equal to radical x for number 1. And what I want us to do is figure out what is g prime of 4 using the rule that g prime of b is equal to 1 over f prime of a. So to find g prime of 4, what we want to do is, since g is the inverse function here, we want to figure out, well, if we're inputting 4 to the inverse, that was an output of the original function. In order to get that reciprocal relationship here, what input for the function f of x would output 4? Well, I mean, you can quickly figure that out, right? If you set those equal, 4 equals x squared, so therefore we're going to get x equals 2. Remember that x is just greater than 0 here. So whatever the slope of the tangent line is at x equals 2 on the original, the reciprocal of that would be the slope at x equals 4 on the inverse. Okay, so let that sentence sink in for a second as to what this relationship is really all about. So do we have f prime of x defined? Not quite yet, but we can write that pretty quickly. F prime of x we know is 2x. So based on that definition, 1 over f prime of 2 would be 1 over 2 times 2. So that would be 1/4. And in a lot of these cases, I'm going to ask you to check this by finding g prime of x and evaluating it at b. Okay, so b in this case is the value x equals 4. So do we really get 1/4 if I find the derivative first? So g prime of x would be 1 over 2 radical x. We know that's the derivative of radical x. If I find g prime of 4, that would be 1 over 2 radical 4, which is 1 over 2 times 2, which is 1/4. Okay. So the nice thing is, you know, if you're saying, well, why can't I do that every time, right? I mean, if this is an easy inverse to find, it's an easy derivative to find, plug it in. Well, you can for ones that we know how to easily find the inverse for. I'll refer you back to that example at the end of the chart to say, wait, what if I don't know how to find the inverse? Or what if it's not easy to find the inverse? Is there a process that I can still evaluate on the inverse function? And the answer is yes. Let's do another one together. Let's try x cubed. Okay, so find g of x. And g of x in these contexts are always going to be the inverse of what we started with. If you switch x and y, you get x equals y cubed there. Cube root both sides to get that g of x is equal to the cube root of x. Remember, we have no domain restrictions to worry about whether or not this function is 1 to 1 over. This is an entirely 1-to-1 function. Okay, so let's find g prime of -8. And we're going to use the rule. So g prime of -8 would equal 1 over f prime. It's the reciprocal slope. We have to figure out what input to the function f of x gives you an output of -8. And that, I think you can probably think of just quickly in your head. If not, of course, you're just going to set -8 equal to x cubed, take the cube root of both sides, and get that x equals -2. So what we know is that the slope of the tangent line on the inverse at -8 is the reciprocal slope when you input -2 to the original function's derivative. So what is the original function's derivative? Well, f prime of x is equal to 3x squared. So we're going to do 1 over 3 times -2 squared. And that's going to be 1 over 3 times 4, which is 1/12. Okay. So now we know the slope of the inverse function at -8. But since we already have defined the inverse equation up here, we can find its derivative and evaluate it at -8 and see what happens. Hopefully we get the same thing. So for g prime of x, given that g of x is the cube root of x, we would get 1/3 x to the subtract 1 -2/3 power. If you want to rewrite that as 1 over 3 times x to the positive 2/3, we can use a positive exponent there. If we evaluate this at -8, we get 1 over 3 times -8 to the 2/3. And let's see. Well, -8 to the 2/3, cube root of -8 is -2. Squared is 4 times 3 is 12 down in the denominator there. Okay, so those do in fact match. All right. Next time we're together, what I think I'll save is these last 2 questions for us to try in class. we'll extend ourselves a little bit further and start talking about inverse of something that is rational. And then we'll go ahead and maybe think about using some rules to find g prime of 2 and using our inverse equation, also do it and from that perspective as well. And then we have one more. This is actually going back to the last one on the chart. Oops, we don't know the inverse, but we can still find the derivative at certain points along the inverse function using the rule that we've now established. So we'll save this for class next time. Make a quick note of that for myself. And that's pretty much it as far as derivatives of inverses are concerned. So if you have any questions, let me know. Otherwise, we'll go over this next time I see you in class. Have a good day.